Okay, are there any questions on your projects related questions, or you guys are putting some time on the project? I think if you don't do that, then you might find it stressful towards the end. So distribute the time over the remaining period of the course. So if there are no questions, let's just continue with the linear algebra portion. So we saw that linear algebra is the basis, the foundation on which simulation tools are built. And we saw direct methods, and we saw iterative methods, and we looked at the eigenvalue problem, particularly how to calculate select eigenvalues from a certain region. And we looked at the spectral representation of the solution. That's going to form the basis for one of the most powerful methods that you will find in COMSOL and a number of other large packages that solve millions of equations, because for a very large system, this turns out to be the most effective method. Direct methods, you simply don't have the storage space to save all the matrix elements, whereas in here, you can get away by defining a very well-defined vector matrix multiplication operation, which can be parallelized as well. So it's one of the important methods, and the idea behind that is also extremely interesting. So let me just talk about the idea with this figure, and then we will go through some of the steps in the algorithm. You will be able to, I have a MATLAB code, so you'll be able to take a copy of that and run it if you like. But MATLAB has a built-in code as well. Okay, so what is the basic idea of a conjugate gradient method? Okay, what is the problem that we are solving? The problem that we are solving is this, AX equal to B. Okay, so we're going to convert that problem into a problem that minimizes a function. Okay, and that function is going to be, maybe I'll show it to you now. It's going to be something like this. Okay, so it's essentially we are forming a scalar objective function from the equation that is given to us, that is AX equal to B. So what we have done is we have pre-multiplied both sides by X transpose so that you get a scalar, and we have 1/2, but that really doesn't matter. It's there for to make the algebra simple. Okay, when you take the derivative of this. So the idea behind constructing a scalar function of a vector field X like this is to claim that minimum of this function is the solution to the AX equal to B. In the last class, we saw that when we are given a non-conforming matrix AX equal to B, where number of rows and columns were not the same. But now, number of rows and columns are the same. AX equal to B has a definite solution, meaning AX minus B should be equal to 0, not the residual that we are trying to minimize. Okay, but we still form this residual, not the residual, the objective function, and minimizing this objective function would be equivalent to solving the original problem. This idea is very powerful. Later on, when we look at go from algebraic equations to differential equations, we will see instead of finding an unknown vector, we will need to find an unknown function. That function that satisfies something like this. What is this? D is some differential operator. It can be a second derivative plus the first derivative operating on U. U is the function. U is a function of X in the one-dimensional case, boundary value problem. And F is a forcing function on the differential equation. So you can see the similarity between solving a differential equation and solving the algebraic equation, AX equal to B, where A is an operator, X is the unknown, B is the forcing vector on this system. In the same way, D is the operator, but it is a differential operator operating on a function U, and it has a forcing function f of x on the right-hand side. So one can form a minimal residual problem, or in some cases you can form equivalent objective function called through variational calculus. Okay, and that is find of all the possible functions ux that which minimizes an integral, an objective function. Minimizing that integral will be the same as satisfying this differential equation. And we will show that in a simple example when we start dealing with differential equations through functional approximations. But I am pointing out the reason why we are going through this. It leads to a very powerful algorithm for solving algebraic equations, but the idea is also easily carried forward to solving ordinary and partial differential equations. Now, why is minimizing this the same as ax equal to b? Can you see it visually from that? What does minimizing that function mean? Setting df dx equal to 0, right? So when you take the derivative of the first term, what do you get? So do you know how to take derivatives of vectors and matrices? So essentially you have to apply the chain rule, right? So you treat this as x times ax. So keep ax constant and take the derivative with respect to x. So what do you get? Derivative of x with respect to x is identity matrix. Because these two are vectors, it's an identity matrix, right? And so that's just going to give you ax, okay? And the right hand side, the derivative of x with respect to x would be, again, the same thing, right? So that's going to give you 1/2 ax, right? And then you need to do this, because it's a quadratic, you need to do it one more time. This time with respect to keeping x transpose a, take the derivative with respect to the x on the right hand side, derivative of x with respect to x, right? So that will also give you identity matrix, okay? Minus b is equal to 0. There will be 1/2. Now you can see why the 1/2 is there, right? Now I should tell you that this method works for symmetric matrices. It was developed for symmetric matrices, okay? The conjugate gradient method. So A is supposed to be symmetric. So you have 1/2 ax, 1/2 x transpose A. If you transpose that, you're going to get ax transpose, right? So when you add that, you're going to get ax minus b equal to 0. So minimizing this automatically is equal to setting ax equal to b, or ax minus b equal to 0, okay? And geometrically, if you want to think about it, this idea is also used for nonlinear problems later on. So suppose I give you a function f of x, just a scalar function. One function, a function of one variable. The function has a behavior like this. So what does f of x equal to 0 mean in this case? Find the value of x that makes f of x equal to 0. No, we are solving for algebraic equation, right? So f of x equal to 0 means it is this point, okay? But what I'm saying is that is the same as minimizing f squared. So if I plot f square versus x, how does that graph look? Because this negative, when you square it, will become positive, right? So this graph will look something like this, perhaps. All the negative values will go to the positive values because I'm squaring it, okay? But this point will become the minimum of the new function. So in fact, fsolve we have used in MATLAB. Fsolve solves problems like this, f of x equal to 0, right? How does it do it? It does exactly the same thing. It squares the function, finds the minimum of that, using the idea of the descent, steepness of descent. Okay? But what you need to do is, when you're using the minimization algorithm, you can get some spurious solutions that are incorrect. Okay, like for example, this is a minimum, but the function is not equal to 0. When you square that, that minimum will still be there, right? So the search algorithm that finds the minimum might find that one, and that won't be the correct solution. So what you need to do is, after you found the minimum, take that value of x and put it and calculate what is the function value. If that function value is not equal to 0, you reject that minimum. That's not correct, right? And you do the search again in a different part of x. And if that minimum gives you the value of x equal to f of x equal to 0, then you found the correct solution to your problem. Yeah.
After we find over forward over H, the matrix dimensions agree, or am I saying it wrong?
The matrix, it's a square symmetric matrix.
I mean, like half AX plus half X transpose A. Do the dimensions agree when we are adding them up? Or is it not necessary?
They do. They both will be column vectors. AX will be a column vector, and X transpose A will also be a column vector. Because this is an n by n, and this is n by 1. Right?
N by 1.
N by 1, right. So there are n equations in a sense.
Okay.
When you say n by 1, there are n rows on one column. There are n equations. So every term in that should have n rows and one column. This is n by n, this is n by 1. So the product is n by 1. Now here you're transposing it, right? So this is 1 by n, and this is n by n.
So it's going to be 1 by n.
Yeah, I guess you need to probably transpose that, right?
So maybe when
I
we
mean-
differentiate the transpose,
Yeah, when you differentiate, I think the transpose has to be, one of the rules of differentiation there, I think, is you need to transpose that also, right? Yeah, I think that's a good observation. I need to verify it. I think that's correct. But that's the only way it will work.
maybe the first one will also be X transpose A, half X transpose A. Because we're differentiating X transpose with respect to X. Maybe I don't know.
Yeah. So there is something I'm missing there. So the first time you're taking the derivative of X transpose with X, and that should be X transpose is a row vector and X is a column vector. So
Maybe we
Because
can
the-
look
the-
at
the
it
whole-
and look it up.
the whole thing should be, you see, this is a scalar function, but you're taking the derivative of the scalar function with respect to a vector. So the result should be a vector, and the result should be a column vector, right? Let me check on this one. What is the rules of operation for derivative and transpose? But that's a good point. Okay, I didn't pay attention to that. I will come back with a clarification in the next class. Okay. So the lesson that we learn from this is, if you're given an algebraic equation, you can construct an objective function that's quadratic of that, square of that in some sense, and minimization of that will give you the same solution to the original problem. And that is what this method is based on. The conjugate gradient method is based on finding the minimum of this scalar function of a vector variable. F is a scalar function. So that scalar function's contours can be plotted, and that's what this graph is. Okay, so this graph is constant values of that function f in a two-dimensional case. So we just have x1 and x2 as the two components. Okay, but you have to imagine that similar contours exist in higher dimension, in 3 dimension, in 4 dimension, etc. So there is the minimum, and that minimum corresponds to ax equal to b. Okay, so we make some arbitrary guess x0. So yeah.
I looked it up. So it says the derivative of X transpose AX equals to X transpose A transpose plus X transpose A.
Thank you. This is the power of internet these days. You don't have to remember anything. You just need to go and.
So it's X transpose times A transpose plus A. Okay. So the X transpose comes in the front and the difference is
So when you take the derivative,
mm-hmm.
yeah, right, yeah. That's where I thought it must be. Thank you. You saved me some verifying that. But you guys can verify this by yourself very easily going into the internet these days. Okay, so the key ideas let me lay out, and then we'll go through the algorithmic details. Okay, so the key idea is we converted this problem into a problem of minimizing this function. Okay, minimizing that function is the same as solving that equation. So that function has contours like this with a minimum somewhere. Okay, so the steepest descent says that I need to find. There are two things that you need to do. You start with some initial guess x0, and in iterative method, the essence of the method is which direction do I go? Where do I make the next guess? Do I just keep guessing arbitrarily, or do I devise an algorithm that is intelligent enough to take me to the solution in the shortest number of guesses, shortest number of iterations? So since I'm looking for minimum, I should go in the direction where the function changes the most. That is why it's called the steepest descent. Okay? So that is one thing. That is the vector. What is the direction of the vector? The direction of the vector is given by gradient of that function f. I can take the gradient of the function because I know what the function is. Okay? So gradient of the function is going to be a vector. So it gives me the direction. The next question that I need to ask is, how far should I go along that direction? Okay? Do I go just one short distance? Like, for example, do I stop here, or do I go all the way somewhere there? Okay? And what do you see here in the graph? If you keep going along this, it keeps decreasing, right? And then you hit kind of minimum on that line, and then it starts increasing because this value is the same as that value, right? So there is, every line that you cut across like that will have a minimum, right? So you need to find the length, appropriate length over which you need to go, and then take a next guess. What would be the next best idea for the next guess? From that point, you look where the steepest direction is. Okay? So again, you take the gradient of that function at that point, and that vector points out in this direction. Okay?
So,
yeah.
So it has to search through every possible vector before it actually makes a decision.
No, that would be one way of doing it. That is, take the vector in many directions and calculate the gradient in each one of them numerically. But if you know the function analytically, you can take the derivative analytically, right? So if the gradient of the function is given to the algorithm analytically, this is how you would do it for nonlinear problems. But for linear problem, it can take the derivative because we just took the derivative. We made some mistakes, but we did take the derivative, right? So it knows what the derivative is, right? So the derivative actually doesn't figure. When you see the algorithm, it just involves, it has been arranged so cleverly, it just involves a matrix multiplication with a series of vectors. These vectors are the vectors that we construct. An arbitrary vector initially, but the next one is going to be in the direction of the steepest descent. Or in this one, what they do is they actually take it in the direction perpendicular to the previous vector. So the Gram-Schmidt procedure that we saw earlier comes in very handy to determine both the length that you need to decide and the direction of the next one. Okay? And using these two ideas alternately, you build an entire algorithm that converges very, very fast. As long as A is symmetric and diagonally dominant, the convergence of this is very fast, and there are mathematical proofs showing why it should converge fast. But if it is non-symmetric and if it is not diagonal dominant simply means the elements on the diagonal are larger than sum of all the elements in any row. Okay? So if it is not, then the method still can be pushed, but you need to use under relaxation factors, etc., during your iteration because the matrix is not well formulated. Okay? So that's a geometrical interpretation or explanation of what the conjugate gradient essentially does. Any questions on that?
So you said we stop at the closest point from solution?
Well, we stop after evaluating the residual. So the residual is evaluated as part of the algorithm. The residual is ax minus b equal to r.
No, not that stop. I mean, when changing the direction.
Oh, to determine how far you need to go? Mm-hmm. That is done by the coefficient that appears in these search direction vectors. So there is, what we are going to do is we are going to take b and express it as alpha k pk. Okay, pk is my search direction vector, and alpha k is a length and I'm going to take. Okay, and so I will find the optimal length I'm going to take as part of the algorithm by implementing this idea that every vector is going to be perpendicular to each other. So if I go in one direction, then at the end of it, I want to take a direction that is perpendicular to that, and keep doing this.
Yeah, for me, it looks like if you go and if you compare with the nearest contour, and when the tangent of the contour is parallel to the line, that's a good place to start.
But for that, you need to know what the contours look like. You don't want to construct.
It's not necessary that the contours always be circular.
Yeah, right. So you want a method that doesn't require a lot of additional computations to find out where the contour is, even though that method will work, but it will become dependent on the problem. Okay. Whereas you want to devise a method that works on any matrix A as long as it meets those two criteria, symmetric and diagonally dominant. And the idea can be extended to nonlinear problems as well. That's one thing with iterative methods. Whatever idea that you develop can easily be applied to nonlinear. Gaussian elimination cannot be applied to nonlinear problems. Yeah.
So, second question, sir. When you have potential energy surfaces, you have metastable states where it's also a minima. Then how do you avoid being stuck over there using conjugate gradient?
This is why I said, where is that graph? The conjugate gradient method doesn't know that you have reached a solution, right? So the conjugate gradient method essentially looks for minima like this. There may be many such minima locally, okay? So that depends on what the function is, particularly for nonlinear problem. For a linear problem, the objective function that we have defined is a quadratic function. X transpose AX minus X transpose B is a quadratic function, so there is only one well-defined minima. Okay, but for a nonlinear problem, when you apply this, very easily you could have this kind of a behavior, and depending on where you start your initial guess, you may get stuck in this minimum. Okay, but you need to, after you found a minimum, you know that it is a minimum, you calculate whether the function is 0. When you calculate the function, you're going to get this value. So the function is not 0, so you know even though that is a minimum of an auxiliary problem that we formulated by simply squaring it, that's not the solution we want. So we throw that away and make another guess. Okay, and until you hit the minimum where the function is equal to 0. Okay. Now this is for solving a set of algebraic equations. Now for a problem of optimization, every one of those minima would be valid, except you need to say what is the global minimum. There you need to do search to find several minima and see which one is a global one. But you were asking about potential energy.
It's
Yeah.
It's like optimization.
It is exactly optimization. Yeah, we are using optimization algorithm here to solve a set of linear or nonlinear algebraic equations. Yeah.
This is better than like bisection method to find.
Oh yeah, bisection method is one of the worst methods that you can have. Easiest to understand, right? But it's it's not very efficient in terms of convergence. The secant method is much better, and Newton method, we're going to see that. Newton method is the best method for nonlinear algebraic equations, and we're going to build some even more powerful algorithms on top of Newton method for that. Okay, so that's the essential idea, to minimize this through a sequence of operations. And the algorithm proceeds like this. You start making an initial guess x0, and you calculate a residual. You call this vector p1, b minus ax0. I don't know whether you can see this. Okay, so here you see. So I can calculate p1. What does it involve? It simply involves b and one vector matrix multiplication, a times x0. x0 is my initial guess. So this is an easy operation. Not inverse, not decomposition, etc. Just a matrix multiplication and subtraction. That gives you P1. Okay? So that gives you the initial direction in which the residual vector is pointing. Okay? And then what we are going to do is we are going to, this idea, I guess I haven't done that yet, right? The idea of what is a conjugate vector. Okay, this is a generalization of the idea of perpendicularity. Two vectors are perpendicular if their inner product is 0. Right? We saw that earlier. So here the inner product is defined in a weighted function. So you can look at u as one vector and v as another vector. We say these two vectors are perpendicular with respect to this weighting matrix A. Okay, and if that product is 0, then u and v are orthogonal. Now, the method of weighted residuals for differential equations uses exactly the same idea. You have a weighting function to take control of balancing the terms that are not of the same order. Okay, so and remember, A is symmetric and positive definite. It simply means it's diagonally dominant. Okay, so the inner product between two vectors u and v are written in this form, u comma v, with respect to the weighting factor A. So the given matrix A itself is used as the weighting factor. And that simply means if you take u and multiply it by A, and the resultant vector, you find the inner product with V, or you take A transpose and multiply it by V, and take the inner product with U, or U with AV, they are all going to be the same. And if that is 0, then we say that these two vectors are perpendicular to each other, the vector u and v. So that's just a generalization of the notion of orthogonality that we saw in constructing Gram-Schmidt procedure 2. So, and we have already seen the spectral representation for the linear algebraic equations. And that is the solution x, here I put a star here to indicate that it's an approximate solution, can be written as a summation of a series of vectors alpha and pi if pi are linearly independent. They form a basis. Okay? And you can orthogonalize it, orthonormalize it, whatever you can do using the Gram-Schmidt procedure. So this is always possible. The solution can be constructed as a linear combination of n vectors that are weighted with respect to the factors alpha. Okay, so we can write then b as equal to a x star, okay, and substitute for x star in here, that is alpha times a times pi. Okay, that's taking the original equation that is given, but x star is an approximate solution in terms of its spectral representation. The approximation will come by not taking all the n terms. If you take all the n terms, and if this is a true basis for your space, then this is an exact solution. This is the spectral representation. Okay, but we're going to not take all the terms, and then the approximation will come. So you have substituting a x star, you get alpha a p, and p multiplied by the p transpose. Okay, and when you do that, you get p transpose b on this side, you get p transpose a x star, and take that inside alpha I p k a p I. Now we know that the set of vectors p are conjugate or orthogonal with respect to this weighting factor a. Okay, so only when I is equal to k, you're going to get a non-zero value. All the other times it will be 0 because of the orthogonality property, right? So we get an equation just in terms of alpha k. That's the way that we find. Of course, you can apply this for each value of k going from 1 to n. So you can find all the n alpha coefficients. Okay, and alpha coefficient is simply given by pkb divided by pka k. Now, if pk is some arbitrary guess that you made, of course, this is not going to be the true solution, and that's why we need an iterative scheme to update that. Okay. So, any questions up to this point? So, this is how we calculate these coefficients in our representation for the solution, and that is nothing but we know the guesses that you make when k equal to 0, the residual ax minus b, and b is known and a is known. So, this is all computed. Alpha can be computed as a number. Okay. Any questions? So the algorithm is put together in the following way. So the residual, k start from 0, that's the first guess. So you make a guess and you calculate the residual. And then you develop an updating procedure for finding the next vector. pk plus 1 is the residual vector minus all these previous vectors. Now we are not going all the way to n. That's why it's an approximate procedure that needs to be repeatedly applied. But this is the formula that we had for alpha. So what does this tell us? Can you interpret this equation? Remember, P0 is my first guess. Right? I make an X0 and I calculate R0 and then I calculate from this one by plugging it into this one. Everything is known. The residual in the first step is known, and P0 is the same as the residual in the first step. So I can calculate P1 and repeat that, calculate P2, etc. Okay, so I is less than K, so you can gradually increase the number of terms it has. So the interpretation for this would be the next vector, the direction for the next vector pk plus 1 is going to be the direction for the previous vector minus all this. I'm subtracting all the components from the previous search directions because I want to go in the new direction. I want to make this perpendicular to all the others. This is the same idea that we use in Grant-Schmidt procedure. Okay, when you construct the second vector to be perpendicular to the first, the third one to be perpendicular to both first and second, and so on. So this summation just keeps on increasing. Okay, and if you do it all the way to n, you will the calculations get more and more complicated, but you include more and more vectors. Normally you don't. You just take a few vectors and then continue the process. Okay, so once you get pk plus 1, that is the direction. Remember, I posed the problem as two questions. One is, what is the next direction? How far should I go in that? So this formula gives us what is the next direction that is perpendicular to the previous direction that you have taken. And then this tells you how long should you take, that is alpha k plus 1. So xk plus 1 should be equal to xk plus, in the new direction, pk plus 1, take as length of alpha k plus 1. How is alpha k plus 1 calculated? The formula that we had derived before, okay, using that. So essentially these two formula give you, this is one step and that's another step. If you put them in a loop, you have the conjugate gradient method. Okay, the first one answers what is the direction, the second one answers how far should I go in that direction, and then keep repeating that. And verifying, in the process you are always calculating R, so you can verify that R is equal to 0 to a certain precision tolerance. So this is the so-called pseudo code where you make a guess x0, calculate your R0, and R0 is set equal to P0 in the first step, and then repeat this. Okay, so you calculate your alpha, you take a certain step in the alpha direction, and you calculate the next vector, Rk plus 1, and keep repeating this. And there is also a MATLAB code that I picked up from web actually. So it's a fairly simple code, and it can solve hundreds of thousands of equations as long as you have a very efficient vector matrix multiplication. Now that's important. Imagine you have a matrix that is 100,000 by 100,000, but only 10% of the elements are not 0. Everything else is 0. Do you want to keep multiplying 0 by 0 to know it is 0? No, you don't want that. So you need to define algorithmically a subroutine that will make this multiplication in the most efficient way. Store only the non-zero elements and take the corresponding elements from the vector P and just multiply those non-zero elements with that. And the efficiency of that comes from how efficient you write that vector matrix multiplication and how effectively you can parallelize that so that you can take, like if you have 100,000 vector and you want to, if it is dense, for example, you want to distribute it to 32 processes, 64 processes, etc. So a lot of effort goes into those aspects. The concept itself is not very difficult to implement. In its simplest form, this is the basic code that will implement a conjugate gradient. Okay, any questions?
So how are you skipping the zeros in that code?
How are we skip? In this code we are not. Okay, so here you are just multiplying A times P. So you're going to take the entire row and the entire column. Now, MATLAB has a sparse tool. So if you store the matrix as sparse matrix, then what it does is it stores only the location I and j and the value s. Then you can write within MATLAB your own function that will just take those elements, corresponding elements, and multiply it. Okay, so that covers essentially linear algebra for algebraic equations. So I want to now talk about differential equations. Again, concepts from linear algebra, but applied to differential equations that will take us towards the path of stability analysis, state space representations, etc. I don't know whether you have seen this. And then we will switch to nonlinear algebraic equations, where the methods that we learn from this will be applicable to understand steady state solutions, multiplicity of solutions. That's one problem we need to deal with when you're dealing with nonlinear equations. For linear equations, there is only one unique solution, as long as the problem is well formulated. Okay? So have you seen this? Should I skip this, or should I go through it in greater detail? So what I'm going to talk about here is how do you solve a set of linear differential equations? How many of you know? It's a matrix problem. So it's not just one equation, but you have a system of equations. You have seen that. Anybody else? You have all seen that. So can I skip that, or? Okay. So you know how the eigenvalue problem comes from this one, right? So essentially you are proposing a solution of this form, e to the power lambda t, and plug it in there. And when you take the derivative on the left-hand side, e to the power lambda t is an eigenfunction. It will give you lambda times e to the power lambda t. That's how you get the eigenvalue problem. So the vectors, you need to find the eigenvectors, and you express the solutions in terms of the eigenvalues and eigenvectors of that matrix. This tells us why the eigenvalue of this is important to determine the stability of this dynamical system. Okay? If the lambda is positive, real part of lambda is positive, you have a solution that blows up in time. The system is unstable. So you need the real part of lambda to be less than 0 for stability. Okay? And when you have a nonlinear system, the problem becomes like this: dx dt equals some function of x. Okay? So you need to linearize that, and when you linearize that, you get an equation like this, and you find the eigenvalues of the linearized system, and that tells you the stability, about the linear stability of that particular problem. That is, to small perturbations, is that nonlinear system stable or unstable? Is answered by the same question. So the eigenvalue problem is an important problem in stability analysis as well, not only in spectral representation of the solution. So I have a series of, this is, as I've said earlier, you have seen this. Essentially, how do you construct x as a function of time? Is expressing it in terms of the eigenvalues and eigenvectors, and these weighting functions are determined from initial conditions using orthogonality condition. So go through that. But from the point of nonlinear dynamics, I want to talk about this trajectories in the so-called state space. Are you guys familiar with that? If you are familiar with that, we can move. Okay, so here I have a 2x2 system. Two equations in two unknowns. x1 and x2 are the unknowns. x1 prime is the derivative. So I have a solution to this problem that is given in the form of here that you see. Okay, so I will have two terms in the series, and I will have two eigenvalues and two eigenvectors. And if both the real part of the eigenvalues are less than 0, it's going to be a stable system. And the trajectory of this will essentially go towards a steady state. Right? So what does a state space mean? It simply means if I have two by two system, x1 and x2 are called the states of a particular system that I'm modeling. For a CSTR problem that you did, for example, temperature and concentration are the two states. So I can plot temperature on one axis, concentration on the other axis, and if I give some initial condition of x at t equal to 0, this trajectory will go something like this and maybe reach a steady state. Okay? So it is this trajectory that is represented by this solution to that particular problem. Okay? So the state space representation of the solution is essentially plotting components of x1, x2, x3, etc. in a multi-dimensional space. So for this particular problem, what do? We go through exactly the procedure that we laid out, find out the eigenvectors, find out the eigenvalues, and you will find that the eigenvalues are, what are they? What do I have? I guess they don't have the values of the eigen. But it turns out that this problem has one eigenvalue that is positive. Okay. Lambda 1 is positive and lambda 2 is negative. How do we know that? We know that by simply plotting the trajectories of x1 and x2 in the state space. This is x1 versus x2. And what you find is, if I start with some initial condition, the trajectory will go something like this. Okay? If I start somewhere here, it will go something like this. Okay? If I start somewhere here, it's going to go like that or like this. Okay? So this is one of the eigenvectors that you see. Okay, and this is the other eigenvector that you see. These are the two eigenvectors. They can be computed, because the matrix is given to you. And what you will see is that one of them is called an attractor, the other one is a repeller, in the sense it is unstable. So if you start anywhere close to this, eventually it will blow away. Okay, but you start here, the attractor tries to bring it to the steady state. This is the steady state. Okay. But if both the eigenvalues were negative, what would happen? No matter where you start, it will be attracted towards that and it will reach a steady state. Okay? But in this case, one is positive and one is negative, and this is the kind of flow that you will get. By simply plotting the slope of x1 prime and x2 prime at different locations. So in MATLAB, you can write a function without even solving for it. All you need to do is, x1 prime, x2 prime. So construct a grid, and at every point calculate x1 prime and x2 prime, and that's a vector. Plot the direction of the vector. Okay, that's the direction in which the trajectory will evolve. And that representation is called the state space representation. It's extremely useful for understanding and interpreting the stability picture of trajectories in a certain state space. Oh, so there are a number of examples like this. So in this case, this is the same example. In the previous case, he just plots out, shows how to plot these vectors. But here you actually calculate the eigenvalues. One is negative, the other one is positive, and you can calculate the two eigenvectors. And what you see is exactly the diagram that we saw earlier. And the solution is given as a linear combination of these two eigenvectors. One of them is negative, that's stable. The other one is positive, that is the unstable mode. So we talk about different modes in the problem, each one corresponding to one eigenvector. So this is a stable mode, that's an unstable mode. Okay? So what would happen if the initial condition is chosen in such a way that it is on the eigenvector corresponding to -1, 1? Okay, the eigenvector corresponding to -1, 1 is this eigenvector, right? Because all the vectors are pointing towards this, and these are pointing towards that. So if I pick my initial condition right on the eigenvector, what would happen? In reality, it will blow up, but the blowing up will be delayed a lot because there is no component of, in the initial condition you have chosen, there is no component of the other vector. It lies on this vector, which means if you go and look at the solution has two components here, right, corresponding to each eigenvalue. So let me just blow this. Okay, so if I pick my initial condition such that the initial vector is aligned with this vector, it's right on that vector, then this has no contribution. So this is an unstable mode, but C2 is equal to 0. from the initial condition. How do you determine C1 and C2? From the initial condition, right? So C2 is equal to 0, and so this one will appear to give you a stable trajectory towards the steady state. But as he pointed out, in real system you always have disturbances, perturbations, and in computers you always have round-off errors. Okay, so they will both eventually contribute tiny amount in this, and all you need is only a tiny amount of departure from that eigenvector. As the trajectory goes along the eigenvector, if you produce a tiny amount of departure from that, the other one will just pull it away. Okay, the other eigenvector. So an unstable system remains an unstable system even if you select your initial condition carefully so that you don't excite the unstable mode. Okay, so some of the terminologies when you read papers, I think these are the terminologies that you'll come across. There is something called a normal mode analysis. Any control person here? Control people do this all the time in the process control, okay, in feedback control, etc. So you do an eigenanalysis, and each mode is you determine how to actually place the eigenvalues. In a control problem, what is the problem? If a system is unstable, you want to stabilize it. That means you want to introduce a control action into the system, dx dt equals ax plus bu. What is u? U is your control action. Okay, so you want to do it in such a way that you move the poles to the left-hand side. You make the system stable through feedback control, for example. Okay, so these concepts mathematically are applicable in a number of different areas, from process control, from hydrodynamic stability theory, nonlinear chaotic dynamics, etc. They're all related. Any questions? Okay, so this is again the picture of the basis, the two eigenvectors forming the basis. The solution is represented in terms of eta 1 and eta 2 as the two eigenvalues. Now, you can have, depending on the matrix A, you can have different types of behavior. Okay, so this is the picture that we saw earlier for this particular problem. So here is another problem. All that changes is the matrix. Okay, and of course the initial condition. Now you have both of them as stable modes. Lambda 1 is -1, lambda 2 is -6. So how do you think that state space representation will look like, the trajectories? Of course, where the two eigenvectors lie, you need to solve for the eigenvectors. Then you can sketch whichever way the two eigenvectors are, okay, the orientation of the eigenvectors. But if it's a stable mode, it's always going to be, no matter where you start, it's always going to be attracted like that towards the steady state. Okay? Now, there are two modes, 1 and 6. So I start somewhere in the space. Can you kind of predict, as the trajectory approaches the steady state, would it be tangent to the eigenvector corresponding to 1 or the eigenvector corresponding to 6, -6? That shows you really you grasp the basic ideas of state space analysis and the time evolution of the trajectory. Do you understand my question? No? So the question that let me explain it in this way. Okay. So in this graph, if I start somewhere here, the trajectory goes like this. Eventually, it goes parallel to the unstable mode. Okay, and if I start right on that, it will go as close as possible, but eventually it will blow away. So the trajectory towards the end is going to be tangential to the unstable mode. But when both are stable, the graph would be, the arrows would be pointing this way. Right? If the arrows are pointed that way, no matter where I start, I'm going to go towards this point. And one corresponds to -6, the other one corresponds to -1. Eigenvalue of -1 and -6. My question is, as these trajectories approach the steady state point, will they be tangent to the -6 eigenvector, or will it be approaching towards -1 tangent?
the dominant eigenvector?
You think -6. You all think that? The answer to that will become clear once you see the solution analytically written down. I hope he has it somewhere. Okay, there is the analytical solution. The first eigenvector is corresponding to -1 with the vector of 1, 4. That means you go in the x direction 1, y direction 4, and then connect the origin. That's the direction of your eigenvector. The second one is -6. This is the so-called fast mode. Okay? That has a direction of -1 and 1. That means take 1 unit left, 1 unit up, draw a line. Okay, that will be your second eigenvector. Do you understand that? So the second one is going to be something like this, corresponding to -6, lambda equal to -6. The first one is going to be 4 units and 1 unit, so it's going to be something like this. This is corresponding to -1. Okay, so the trajectories are going to approach the origin in all cases. The question is it going to approach tangentially to -6 eigenvector or tangential to -1 eigenvector?
Is it 1 for the other sleeper arm? 1 to the right and first the counter.
So the signs,
Yeah.
So the signs over here are the directions of the vector, right?
The vector doesn't have just a direct, I mean, it has an orientation, but it's not whether it is pointing upwards or backwards, it doesn't matter. That sign you can absorb outside. Okay? So this essentially says if you go 1 unit left, 1 unit up, take a point and connect that, that is the direction of that eigenvector. Here 1 unit right and 4 unit. I made 4 and 1, that's a mistake. You go 1 and 4. Okay? So that will be the eigenvector corresponding to -6. But imagine what would happen to these two terms as time goes to infinity. Which one will go to 0 first?
The second one.
The second one, right? Because it has a fast response, right? So this will go to 0. That means the trajectory is going to be governed in a long time by this one. So it will go tangential to in the direction of the slowest eigenvector, right? So by kind of thinking about these, you get a good appreciation in terms of interpreting the physics behind the dynamics of these systems. So here, the actual correct eigenvectors, right? 1 unit left, 1 unit up, and 1 unit right, 4 units up. So these are the two eigenvectors, right? And how does the trajectory look? So the trajectory looks like this. So the fast component essentially is taken out, and then it goes towards the slope component. Okay? So no matter where you start, these are nice to understand for a 2-dimensional system. As you go to 3 and 4 dimensions, you cannot construct this graphical representation, but you can imagine in your mind when you're talking about fast mode or a slow mode, which direction the trajectory will go.
Like since its decay is fast, it's gonna bring the value to stability fast.
That becomes irrelevant. As t goes to infinity, that term drops out. So it is the other term, it's the slowest term that determines when you reach the steady state. Yeah. I think that's the intuition. I also had difficulty. That's why I'm bringing it out, to make sure that you can think about it in the right way. Right? And this is beautifully done for chemical engineers in an article that came in the 62 or 63 by Y and Prater. It's about 130-page article in Advances in Chemical Engineering. It's a beautiful illustration of linear algebra and eigenvalue problem as applied to reaction engineering. So they just consider a set of n reactions, monomolecular reactions, and formulate the problem. You get exactly the same set of ordinary differential equations. And then the equilibrium state, when the reaction goes to 0, is one of the eigenvectors and eigenvalues, the 0 eigenvalue. And then they show the concentration path. So you can give it more meaning. So these trajectories in those cases are the paths of concentration with respect to time. And so it's a nice blend of mathematics and physical intuition as applied to chemical reaction engineering. Okay, so the next thing, I guess, again, you may be familiar with this. If you're given a second order equation, how does the analysis change? We have already talked about it earlier. can always convert the second order system to first order systems. You can find a characteristic root. There will be two eigenvalues, but if you convert it to the system of first order equation, you'll have exactly the same problem, two eigenvalues, and the solution is given in the same way. Okay, so that's just an illustration of how to convert and handle a second order problem. The case of complex eigenvalues. What happens if the eigenvalue is something like this? Okay, plus or minus 3 square root of 3i. Okay. So what do you think would happen in this case?
No real part.
With no real part. There is only imaginary part. Right? So there are two eigenvalues. It's a second order problem. So two eigenvalues that are given by plus and minus, but they are imaginary. 3 square root of 3. So you are still going to write the solution as e to the power lambda t. But what is e to the power lambda t with an imaginary part? It's sine and I cosine, right? It's expressed in terms of sines and cosines.
It's marginally stable.
It's we need to now look at notion of what stability is, right? And we will see a good example very soon. The notion of stability so far has been either it goes to steady state or it blows up. In this case, it does neither. It just goes in circles, right? So you would call this as an equilibrium state, right? That is stable. And if you start anywhere outside of that circle, you'll be attracted to that circle if you have a real part, right? But in this case, the solution is given only in terms of sines and cosines. So there you have the solution. Okay, and how does the trajectory look? I guess I hope they have. I guess they don't have that. No, they do. There. Okay, so it's a closed trajectory. So no matter where you start with your initial condition, you will place the trajectory on the initial condition forever. Okay, this is because it's a purely imaginary pair of eigenvalues. Okay, the translation of this to nonlinear problems is what we call a limit cycle. So in a limit cycle, you start wherever in the initial condition, you'll be attracted to a single trajectory, a closed trajectory. If that happens, you call it as a steady, stable limit cycle. But there are unstable limit cycles as well as solutions to the nonlinear differential equations. So this is just a summary of a node that is unstable, a node that is kind of asymptotically stable. Asymptotic stability means as time goes to zero, it is attracted to the steady state. So this is a case where you have, I guess both are unstable. So no matter where you start, it just goes away, diverges. An asymptotically stable one. But I think in these cases, there are degenerate cases. There are two eigenvalues that become the same, negative or positive. So it's a nice summary of all the possible responses in the state space. So this is, I guess we already seen that. It's, one stable and one unstable. No? And this is called a stable center. That is a pure imaginary eigenvalue. That gives you closed cycles. And a spiral that is unstable, that simply means it has a real part that is positive and an imaginary part that's whatever it is. That gives you the cyclical portion. Whereas this one is a stable spiral. Okay, so that means its real part is negative. But it has a strong imaginary part that forms the circles. So these responses are extremely useful when you're interpreting the results from a simulation. Okay, to know whether the system is stable, whether it has switched from one stable system to another stable system. We spent some time already talking about stability when we looked at the model equations. So we also talked about linear stability of stationary states, and that is given by the sign of the eigenvalue that we've seen before. So this is where I wanted to introduce this new notion of Lyapunov stability. Have you heard of this before? Okay, so this is a very nice generalization of the idea of stability to nonlinear systems. So far we talked about x dot equals ax plus b, but now I have x dot equals some nonlinear function of x as a function of t with an initial condition. Okay? So it's a strictly mathematical definition proposed by Russian mathematician Lyapunov, and we want to develop a geometrical picture of what it means. Okay, and there are slight 2 or 3 variations on that. Okay, so the first one, it says the equilibrium of the above system is said to be stable, Lyapunov stable. Okay, if for every epsilon greater than 0 there exists a delta which is a function of epsilon also greater than 0, such that xe minus x0 is always bounded. That's a mathematical way of stating that. What does it mean visually, geometrically? You can give that in a state space. Okay, so if this is x1 and x2 in a 2-dimensional space, if the steady state is somewhere here, that is what we call xe. Okay, that you see, and x0 is some initial condition that you give. The question is, will the trajectory remain bounded as it goes from this to this? It may not even go to xe, but it may be just circling around it. So we want to generalize the notion of stability. So even the case where we had just a cycle like this, closed, as long as you can put a bound around that, it says that the trajectory will remain bounded, and that would mean it is Lyapunov stable. Okay. So what does this mean? It simply means you can, the difference, the distance between x0 and xe, the norm of that, is bounded by some region delta. So you can draw a circle with a radius of delta, and the trajectory will remain forever in that bound. And this bound you can find for every epsilon that you choose, arbitrary epsilon that you choose. So the bound will be a function of this epsilon. Now, what is that epsilon? That epsilon simply is the difference between the equilibrium state and the point on the trajectory. Okay? So, essentially, a general notion of when a system is stable, as long as it doesn't blow away, it wanders in a space. Remember the Lorentz equation that we saw. In one of the examples, I think you solved that, right? What does the Lorentz equation do? If you keep increasing the forcing, it gives you a strange attractor. So the trajectory never closes on itself. It's not a limit cycle. Never goes to a steady state, but it wanders in a space, but in a subspace. It doesn't blow up, right? So when you have that kind of a behavior, you can always bound that by a region delta, and the system will be considered as stable. But it is not steady state. The time series is erratic, but it remains bounded. So that is essentially what this says. If the system is bounded, then it is stable. The next variation of this one is asymptotically stable. So this one says it's not only bounded and it's not just wandering, but it is going towards 0. As t goes to infinity, the difference between the trajectory and the equilibrium point goes to 0. In the previous case, it remains bounded. In this case, it goes to 0. Okay? And the third one is exponentially stable, which says that it not only goes to 0, it goes to 0 in an exponentially decaying fashion, e to the power minus t. Now, these are all nice conceptual definitions of what a stability is. That's applicable for qualitative analysis of trajectories to determine whether a given differential equation, a given model is stable or not without solving for the trajectory. All the previous cases that we saw, they were linear systems, or if it is non-linear system, we're going to linearize it, and we can say something about the stability of it in the linear sense by solving for the eigenvalues. You need to solve for the eigenvalues. Okay? And we saw that when you have 100,000 equations, you cannot solve for all eigenvalues. We've seen algorithms to pick those that are close to the margin of stability. Right? Now, this method tells us how to say something about the stability of the system by only knowing the function f, not the solution x. I don't need to construct the solution x, but I want to be able to say whether the system is going to be stable or not by examining F. And in the 60s and 70s, there were a lot of activities trying to construct the so-called Lyapunov function that will identify regions of stability for reactors. Chemical engineers got involved. In fact, my supervisor at Princeton did a lot of work on this area, published regions of stability for various reactor models using the Lyapunov stability concept. So here I am just laying out in plain language what I just told you. But let's look at this so-called method of second method for stability. How do we find the stability of a particular system? There's a very nice concept behind this. And the concept is you need to construct a function v of x, a scalar function. X is a vector, but you need to construct a scalar function, and that maps essentially from Rn to R. Simply means from a vector, you're going to calculate a scalar number. From a vector, n-dimensional vector, you're going to calculate a scalar number. The stability requirement, according to the previous definition, is that this v of x must be greater than or equal to 0. It means it must be positive definite in the region that you are interested in. And its derivative, v dot, calculated as ddt of v of x, must be negative definite, meaning it must be negative in that region where the equilibrium solution is. If you can find such a function for that particular problem, then you are guaranteed stability. Okay? And that's what the Lyapunov's method of construction and proof is centered around. So v of x is called the Lyapunov function, and it doesn't tell us how to go and find that function. That's the problem, because we don't know the solution. We're trying to say something about stability of a model without actually solving it. If you solve it, you know whether it's stable or not, right? So we're trying to develop a qualitative method without solving it by constructing a function that has these properties. And as I said, that was the essence of research for constructing such functions for CSTRs and other models that came out in chemical reaction engineering. But there are some nice examples that I took from a book on the net. So this is given the function dy dt equals f of y, that is the model. Okay, dv dt, we want the derivative to be negative definite, right? So the condition is that we have to apply the chain rule, because v is a function of x, x is a function of t. So it is gradient of v dotted with f. F is dy dt on dx. Okay. So if we can construct a function and take its gradient dotted with f, which is known, and show that it is less than 0, you have guaranteed stability in the Lyapunov sense. But what is the physical meaning of this? The essential idea here is V is, I think some of you that talked about energy minimization idea. This V of x is some sort of an energy representation for the state. Okay, so it could be a potential energy, it could be kinetic energy. You construct that function that says that the energy function has a minimum. Okay, so if it goes to the minimum of that energy function, that means it has a stable solution. Okay, and in that interpretation, there is one simple example that I will give you, and then here is a second order system. Y prime equals z and z prime equals minus y minus 2z. You can write that in a vector matrix form like this. And you take v as a function of state. The states here are y and z. Y and z. Okay? As y squared plus z squared. So it's like a kinetic energy of the system. If x, y, and z are velocities, or to think of them in a two-dimensional space, then y squared plus z squared over 2 is like the kinetic energy. And then you can strictly apply that rule. dv dt is gradient of v multiplied by f, and you'll find that it is minus 2z squared. You can explicitly compute this for a simple problem like this. It's a linear linear differential equation. So z squared is always positive, so this is always negative. So that system is going to be stable. I can claim that without solving for the eigenvalues of this. Because I have constructed by inspection, by intuition, whatever it is, a function v, the Lyapunov function, that has this property that dv et is less than 0 and v is greater than 0, because y and z are they are squared, right? So this function meets those two criteria. This is positive definite, its derivative is negative definite. So without solving that equation, I make the claim that it is stable. And of course, you can verify in this case by solving for the eigenvalues. That's the power of these qualitative methods. But the challenge is in coming up with the correct function for v. So for real nonlinear problems, how people approach this is they will take some function and identify the region in which these conditions are satisfied in the state space and call that region as the region of stability, region of attraction. If your initial condition lies anywhere within that, you will be attracted to that steady state, around that steady state. Is that concept of region of attraction and stability kind of clear? Okay. So this problem illustrates what is that region of attraction for a more complicated nonlinear problem. Now this is a single equation, and it's a nonlinear equation, cubic. Okay? And for this one, it's possible to construct a solution. But remember, our idea is not construct the solution and say something about stability. I guess what else do I have? Linearization I was going to talk about. Okay, let's talk about solving nonlinear algebraic equations. So you have n equations in n unknowns, but f is some nonlinear function. What is the best method to solve by a trial and error guess solution, iterative method? So that is the Newton method. Okay, are you all familiar with the Newton method, right? So the Newton method essentially is x at n plus 1 is equal to x at n minus j inverse f. Okay, so n going from 0, 1, etc. Now the Newton method converges how fast? You're familiar only with the method, not about convergence. It converges quadratically. What is J inverse? J inverse is the so-called Jacobian matrix. Okay, so it is all the derivatives of f with respect to x. Remember, you have f is a vector consisting of f1, f2, fn. There are n functions, and there are n variables. X is a vector consisting of x1, x2, all the way to xn. So you need to take the derivative of f1 with respect to x1, f1 with respect to x2. It's an n by n matrix. Okay? So you need to calculate this Jacobian. You need to make a guess, and the Jacobian has to be calculated at that guess. And you also need to calculate the function at the guess. Okay? And when the function is 0, what happens? This term drops out, and your guess value is the same as the next guess. That means you have converged. Okay? So you monitor the convergence by simply monitoring the norm of this vector f. If that is less than 10 to the minus 9 and minus 12 or something, you stop the iteration. Otherwise, you take the new value, put it back, and update your Jacobian matrix and update your function and repeat that. You have seen that, right? Anybody not seen this one? What is the idea behind that? How do you derive that? How did we come up with this formula? Of course, Newton came up with lots of formulas that nobody else knew, so he might have just come up. I mean, if you ask the same question, how did you come up with this f equals ma? I'm not sure whether he has an answer for that. But this one, there is an answer. The answer is Taylor series expansion. Have you seen that one? It's very important to learn how to derive these algorithms from Taylor series expansion, because that's going to be revisited when we do method of finite differences. It's based on Taylor series expansion. So, yeah, Yeah, essentially you do a Taylor series expansion of the function f of x with a perturbation delta. So f of x plus delta is equal to f of x plus df dx evaluated at that x multiplied by delta plus all the higher order terms in the series, the second derivative, the third derivative, etc. But we don't include that in the Newton method. We drop that. Okay? So f of x plus delta is equal to f of x plus the Jacobian matrix. This is where the Jacobian comes in. Multiplied by delta. Delta is the perturbation from the current guess. Okay? So what do you want this to be? You want this to be 0. Right? So the algorithm says, graphically, if you want to think about it in one-dimensional case, if I have a function like this, and this is my initial guess x, and I'm saying I'm going to draw a tangent to that, and I'm going to approximate the function. The function is actually complicated like this, but I'm going to approximate that function by a tangent. That's why I'm ignoring all the quadratic terms that are above. So this is a linear equation. And I'm going to ask the question, how far should I go from this? So this is delta. So that that tangent goes to 0. That tangent intersects at 0. Because this tangent is my approximation to the function now in the Newton method. Okay? So I ask the question, what should be delta, so that what should this distance be so that the function at f of x plus delta is 0. So I set this equal to 0 and I solve for delta. Okay? And that delta is going to be minus j inverse f. Do you see that? So essentially I'm rearranging this. I'm pushing this to the other side so it becomes minus, and you take this, the inverse. So j inverse f is the delta. Delta is the correction I am making to my initial guess. So this plus the correction vector gives me the new vector. So now with the new value, I'll take its tangent from here and ask where is that tangent intersect the x-axis, and repeat that process. So that's a geometrical interpretation of the Taylor series, and that is actually the algorithm. Okay? Now, I said earlier that solving a set of linear algebraic equations is the most important part. What do you get here? The need to solve a system of linear algebraic equations. What is this? This is nothing but, you can look at it as j delta equals minus f. J is known, f is known, you're solving for delta, right? So you can use the LU decomposition, you can use all the tools to invert this matrix J to solve this linear problem. But this linear problem has to be solved many, many times for a nonlinear algebraic equation. Okay? And that's why it's so important to have a linear solver that is extremely efficient, because that algorithm will be called millions of times when you're solving a nonlinear problem. Okay, so that's a simple idea, but it converges quadratically. I said it converges quadratically. What does that mean? It means if you plot delta, which is your error, the correction that you are making, against the iteration number, you're going to get something like this, delta square, the error square. So if the delta, for example, if the error at some iteration is 10 to the minus 3, you do one more iteration, it goes to 10 to the minus 6. You do one more iteration, it goes to 10 to the minus 12. So it's extremely rapid in convergence, as opposed to the earlier method that we saw, conjugate gradient method. Okay, even though conjugate gradient is an effective method, particularly for very large systems, you may use conjugate gradient method to solve this linear system still, actually using LU decomposition if J is very large. Okay, but applying the Newton method to the nonlinear problem gives you quadratic convergence. And you can prove that for a one-dimensional system using the fixed point iteration concept. Okay, but to solve this, you need to come up with an initial guess. Okay, because you need, when n is equal to 0, you need to come up with an initial guess. And nonlinear problems are notorious for blowing up due to numerical problems, instabilities, if the initial guess is not close enough to the final result. So in the next class, we will look at how we can improve upon the Newton method in terms of Euler-Newton continuation, which is built into COMSOL. And recently, I think, within the last 5 years or so. But these algorithms came into fore probably 10, 15 years ago. So we will see a series of methods for looking at advanced algorithms for solving a set of nonlinear algebraic equations. Once we do that, we move on to functional approximation. That will set the stage for differential equations. Now, reminder, Monday I'm not here. Okay, so we don't have a class on Monday. So we'll meet Wednesday next time, and then we will schedule a time on Friday perhaps that week to catch up on the last class. Okay?
Friday same time, or we can make it earlier?
Do you want to fix it right now? Well, Friday,
We have seminars.
we have seminars, right? So
What time is the seminar for time?
2 o'clock, 2 to 3.
But I don't know.
Do you know whether you have a seminar? Would morning work, Friday morning?
No, I have a seminar.
What time?
9 a.m.
9. Would 10 o'clock work? 10:30?
9 a.m. to 10:30.
10:30 to 12? Would that work? No, sorry, I'm scheduled for advising that week. We will meet on 22nd as scheduled, and then we will try to find a time at that time. Okay, just think about possible times. Okay.
Is it 24?
Yeah,
Do the seminar.
that is okay.
This Friday,